So, class of service. Let's take a look at this concept of class of service and find out what we use this for. So, we're going to describe the purpose and the benefits of class of service. Let's then explain the various components and implement and verify proper operation of class of service. So first of all, let's take a look at the concept here. First of all, let's look at a scenario where we have got different types of traffic going on our network. Now, this is going to be a fairly common type of scenario, particularly with networks today, where we have got maybe voice, maybe video, and of course, we've got data. So here we are, we have a network, we've got unified comms set up on it, we've got a voice server on that. So we've got people in our organization that are making VoIP calls on their VoIP phones, communicating across our network. We may be doing some video conferencing as part of that as well. So maybe we've actually got video links where we're doing we're collaborating with teams of people that may be located in different geographical locations. So we've got remote teams. It's quite common now where you might have people that are part of your team that maybe they're working from home, maybe they're actually located in a different country. So you've got these team things going on where you're having meetings with your teams. And of course, you've got your regular data where you're accessing files off a file server, accessing data off websites, off web servers, off databases, etc. So essentially, what we have is different types of traffic. So let's have a think about what happens. So on a network, when we start to experience congestion on our network. Now, the thing about the way that network traffic tends to work is that it's very burst orientated. So it doesn't just flow along at a nice little standard pace. You get bursts of traffic. And this is in many ways to do with the way that servers work, in that you'll ask for a file off a server, it will get the request and it'll throw that information back at you, and then it will wait for another request and it'll throw that information out. So servers kind of work in a kind of a bursty sort of a way. You suddenly get a big burst of traffic and then sort of goes down to not much, and another big burst. So what can very easily happen on a network is that you can reach your maximum bandwidth with these big bursts of traffic that come across a network. What does that mean? What does reaching a maximum bandwidth actually look like? What is it that determines when we have consumed all of our bandwidth and start dropping traffic? Start dropping traffic. Well, really, it's the way that the interfaces on our intermediate devices are working. So we're sending more traffic into a router or a network device than that device can handle. That's when essentially we start dropping traffic due to congestion. So a router interface, how does it work? Traffic comes in to a router interface, and a router interface has got a little bit of memory in it, which is called a buffer. So the traffic arrives, it goes into a buffer, and then that traffic is then processed by the router. So we have exceeded our bandwidth when the buffer is full. So when traffic's arriving, the buffer is full, and more traffic arrives, that traffic gets dropped. Okay, so basically that's when we start dropping packets. Now, the thing about a telecommunications network, like an ISP or any other telecommunications network, is that it is never economically viable to build a telecommunications network that is able to handle all the traffic that all the subscribers may want to send all the time. You just can't build one economically. So what does that mean? That means that inevitably there will be congestion. It's inevitable. At some point, at some times, there will be congestion on a network, particularly on a telecommunications carrier's network. There will be congestion, and when there's congestion, packets will be dropped. That's the inevitable consequence. of that type of design, and that is and that type of design is normal. Okay, so what I'm saying is that congestion is normal. You are always going to get it, and when you get it, packets will be dropped. So let's have a think about what happens. What effect does that have on the user experience? Okay, so what happens if I am downloading some data off a website, off a server somewhere, opening a web page, whatever I'm doing? What happens if I'm doing that and packets start to be dropped? What effect does that have on that user's experience? Somebody tell me what will happen. The network's congested. I'm trying to open a website. How does that affect my experience as a user? What would happen? Would it open? Eventually, it would. Okay, eventually, it will probably open. All right, eventually. Why? Because I'm not dropping every single packet. I'm just dropping the packets that are arriving at the interface when the interface happens to be full. The buffers happen to be full. In other words, I've exceeded all my available bandwidth. So what does TCP do when we lose a packet in transit? What happens? So I'm opening a website. I'm using port 80, so we're using TCP as a transport protocol. What happens when we lose a packet? What does TCP do with that connection? So I've got a connection to my web server. Here I am on my client. There's congestion on the network in between. Some packets get dropped. What happens next? How do we deal with that? Any ideas? TCP is looking for the next sequence number. It doesn't get it. So we're counting the segments, and we have one missing. What does it do? It asks for it again. So ultimately, that packet will be resent by my server. So it gets dropped. TCP says, "Hey, I missed part of that, or I missed a few packets." It will just request for them to be sent again, and then it will reorder them, and there you go. You're going to get your web page. Or if you're downloading a file, you get your file, or whatever it is that you're doing. So TCP, which is a reliable transport protocol, will take care of the missing bits. It will ask for them again, and you will just have to wait around while that happens, won't you? You just wait around thinking, oh gosh, my website's slow today, the internet's slow today, and you just have to wait around for that to happen. Now, I know you've all experienced that, right? There are certain times of the day when you will notice that the internet just goes slower than at other times, right? So basically, if you jump on the internet at the same time that all the gamers in your neighborhood have jumped on the internet and start gaming, you will notice that the internet goes significantly slower. Why? Because they're consuming all the bandwidth. Okay, so basically there are times when congestion will occur, you will notice it, and the user experience is it goes slower. Okay, it goes slower. The file downloads slower, the website opens slower, whatever it is. So basically it goes slower. Okay, it's a little frustrating, but okay, we still get there eventually. Okay, maybe we have to wait a few more seconds for it to open, but you know, we'll eventually get there. Okay, let's look at this scenario. We're making a voice call. Same situation occurs. Congestion's on the network, we start dropping packets. What is the user experience? What transport protocol are we using at layer 4? What are we running at layer 4? UDP, yeah, we're running UDP. So what does UDP do when we start losing packets? It does nothing. Yeah, it doesn't ask for them again. It's like, too bad, so sad, those packets are gone. Oh well, never mind. Okay, well, forget about that. So it does nothing. It does nothing. So if we start losing packets on a voice call, what the user experience is a drop in the quality of the call. Okay, we start to have bad voice communications. All right, so the call quality goes down. So if we just compare the two experiences, we've got someone accessing a website, it takes a few seconds longer. Oh well, I still got there, not so bad. Someone's on a voice call and we can't understand what the other person's saying because the quality of the call has dropped. That user's experience is quite different to the other user's experience. One user, okay, a little bit slow today, not too bad. The other user, now I can't make a proper phone call because I'm having trouble understanding what the other person is saying. Okay, so you experience a significant impact on the user experience with one type of traffic you experience a far less impact on the user experience with another type of traffic. So what we're saying is some types of traffic, as far as the user experience goes, are very sensitive to the quality of the network in that they cannot tolerate packet loss, and they also can't tolerate delays in the transmission of traffic either. Okay, so they're very sensitive, very time sensitive, very loss sensitive. Same goes for video. You start to, you're having a video conference and you start losing video packets, you will notice a drop in the quality of the video that you're getting. Okay, so what we're saying is that congestion affects the user experience in different ways depending on the type of traffic that's being transmitted or that user is actually consuming. So how do we deal with that? Well, a way of dealing with that is by implementing class of service. And with class of service, what we're able to do is we're able to give different priorities to different type of traffic. So we're able to identify the fact that, okay, we've got a particular type of traffic. We've got video traffic, as the case may be, or voice traffic, or data traffic. And by allocating a different priority to that traffic over other traffic. So what does that mean? That means that when congestion occurs, this doesn't stop congestion, but when congestion occurs, it allows us to influence which packets get dropped. So our voice traffic will go through, our data traffic will get dropped. Or our video traffic will go through, our data traffic will get dropped. So we can influence what gets dropped. Okay, so it meets the network's performance requirements by prioritizing latency-sensitive traffic such as VoIP, controlling congestion to ensure service level agreement maintenance. Now, this service level agreement maintenance is a thing which is particularly relevant to a service provider or internet or a carrier, an internet service provider will have certain agreements in place with their customers to ensure that traffic gets passed. For example, there are things which are known as a guarantee, like you might buy a guaranteed bandwidth from a particular carrier, which means that I can always be assured that a particular amount of traffic will always be passed by that particular carrier. And carriers will sell that. For example, the NBN. With the NBN, you can buy a class of traffic which is voice traffic. So just say I am a provider of internet telephony and I want to provide internet telephony to a range of customers that are connected to the NBN. The NBN will sell me a class of traffic for voice which guarantees a certain amount of bandwidth for that class of traffic. Okay, so what they will do is they will implement class of service on their network to make sure that I always get a certain bandwidth for that class of traffic. I have a service level agreement. So as a carrier, this class of service allows them to meet those contractual arrangements. Allocating bandwidth for different classes of traffic. So we can say that Voice traffic has a certain bandwidth allocation. Data traffic has a certain bandwidth allocation. And we can just make sure that we always allocate that type of bandwidth. So as a customer of an internet service provider, how does this affect you? Let's just say, for example, you've got a head office, you've got a branch office, you know that you want to have a link between the two, obviously. And you know that, of course, there's going to be data that's going across that link. There's going to be people in the branch office accessing maybe file servers, maybe other types of web servers, whatever, at the head office. You also know that there will be phone calls going between the two. You might have a VoIP server at the head office, another VoIP server down at the branch office, and you'll set up a trunk between them so that the calls that are going from the head office to the branch office will go down that trunk. That trunk will go across your VPN. There may be video conferencing that goes on as well. So you want to ensure, so there's a couple of things. You could just go and buy massive amounts of bandwidth and say, oh, this will give us lots of bandwidth so we never have congestion. That may not be a very economical solution. Alternatively, you could say, well, let's go for a much more economical amount of bandwidth that we're buying from this carrier, but let's ask the carrier to implement class of service so that my voice traffic is prioritized over video traffic and also prioritized over, say, data traffic. And you could put that in place so that what would happen then is your carrier would then prioritize that traffic. So even though there may be times when congestion occurs, you'll always be able to make a good quality phone call across that network. And you can implement the same concept in your own network, your own local network that you're building for your organization. You implement this class of service. Okay, so understanding that this is available to you is an important aspect of network design. Okay, so we can have different types of traffic. So we set up this thing called forwarding classes. These identify classes of traffic that should receive common treatment, and we use those to assign traffic to queues, output queues. We have a thing called, there's another thing we can set up called loss priority. Loss priority identifies the priority that a system should give to dropping a packet. That particular priority is used to select the drop profile used in the RED process. Now, the RED stands for Random Early Detection. So what it is, what this RED process does is it monitors the consumption of bandwidth on the network. And if we're getting close to exceeding our maximum bandwidth, what RED does is it starts to preemptively drop packets off of a network. Okay, now one of the problems that you get with a protocol like TCP is that it's kind of like when you have a congestion on the road. Who's ever been on the road where you're getting congestion, the road's getting full? What actually happens? What happens when there's a whole bunch of traffic on the road? You're driving up the highway on the way to Brisbane, and suddenly you get congestion. What happens? Well, the first thing that happens is you're driving along at 100 k's, and suddenly you end up stopping. Right? That's the first thing that happens. The next thing that happens is suddenly you go, and usually the next thing that happens is suddenly you stop again, and then suddenly you go again, and then suddenly you stop again. That's what usually happens, okay? What doesn't happen is, oh, the road's getting full, let's all slow down to an even 40 kilometers an hour. That's what doesn't happen. It'd be nice if that did happen, but generally that doesn't happen. So what this, and that's kind of a bit like what TCP does. What TCP does, it says, okay, it has this thing called a window size, right? So it says, hey, all is good. Let's increase my window size so you can send more traffic. And then it starts noticing that was getting congestion and some of the segments are being lost. And it says, uh-oh, let's reduce our window size. So it sends information back, says reduce the window size and slow everything down. So then the traffic slows down, everything slows down, and then it says, oh, everything's going well again. Let's increase the window size and speed everything up. So what happens is it'll speed everything up, hit the bandwidth limit, slow everything down, everything going really slow, speed everything up again, hit the bandwidth limit, slow everything down again. So basically it's a bit like that congestion on the road where you're going along, suddenly you grind to a halt, and then you suddenly start going again, then you grind to a halt again, and you start going again. Okay, so what that does is it's a very inefficient use of the available bandwidth because we're slowing everything down, not using our bandwidth, speeding everything up, basically consuming all of it and dropping packets and then slowing everything down again. So to overcome that tendency, which is built into how TCP works, to overcome that tendency, there's this algorithm, this RED algorithm, monitors the network for traffic. When it's getting close to hitting its bandwidth limit, what it does is it starts dropping packets off the network. Now, how does it decide what packets to drop? It looks at this thing called loss priority. So we're able to actually put a marking onto a packet, which is its loss priority, and packets that have the greatest loss priority are the ones that get chucked off first. Okay, so they basically get wiped out first. So it's a little bit like you're driving along the highway and we're about to have congestion. But before congestion occurs, cars with the greatest loss priority are put off the road. So we might say, okay, all of the red cars have the greatest loss priority. You're in a red car, you get off the road. And everybody else in every other color car is fine. So basically what we're doing is before we hit congestion, we're clearing the traffic off so we never actually hit congestion. So we're always able to travel along at a nice pace without ever getting that stop-start scenario. So RED, random move detection, is an algorithm that looks at that. And it's quite a configurable algorithm as to how you have it work. But one of the inputs into it is this loss priority. Okay, so what it means is you can mark up a packet saying you've got a bigger loss priority than another packet. So we can say, well, the data packets have got a greater loss priority than the VoIP packets. So if we're starting to hit congestion, we'll drop our data packets first, and then we'll let our VoIP packets go through. Okay, so that's one of the things that we can do, and this is one of the things that you might see. And we looked at firewall filters. We're looking at firewall filters. One of the things that we could do with a firewall filter is you can actually mark up a couple of things. You can mark up a class of service, or you can mark up a loss priority on a packet. One of the other things that telecommunications companies do is they say, we'll guarantee you a certain bandwidth, but anything that goes over that bandwidth, we may or may not pass. So they will put like a policer on your connection, and they will say, okay, well, everything up to a certain amount is fine. But if it goes over that amount, we're going to mark up, we're going to change the loss priority on traffic that goes over a certain bandwidth, so that if our network is going well, with no congestion on our network, your traffic will get passed. But as soon as we get congestion on our network, bang, we're going to dump that extra traffic that goes over that guaranteed bandwidth limit. That's going to get dropped straight away. So that's how quite often carriers work. You have a committed information rate, and then you have a maximum information rate. And anything in between those is maybe we'll deliver it, providing there's no congestion on our network. And the way that they achieve that often is by setting a loss priority on that additional traffic. Okay, let's have a bit of a look at an overview of processing here. So the whole process is traffic enters our network. We have this BA, but BA stands for behavioral aggregate. So it's a classifier. So it looks at what type of traffic is this? Is it voice? Is it data? What is it? What type of traffic is it? And it will then classify the traffic. It will then implement a forwarding class for the traffic and give it a loss priority based on its classification. Okay, so forwarding classes and loss priority. Forwarding classes will determine ultimately the queue that it goes into. So we'll have a queue for voice, a queue for data, a queue for video. And then what we can do with our queues is we can give priorities to different queues. So different queues have priority over other queues, so that when we've got, and these queues are sitting in our buffer, in our router. So they're occupying the memory space in our buffer. So we'll service certain queues before others. So those queues that are not being serviced, if they just fill up and that type of traffic arrives, well, too bad. That traffic will get dropped. So we're servicing these different queues in our router. So we then have these policing policies, which says, okay, if you get traffic over a certain bandwidth, then we may change the forwarding class. We might say, okay, happy days. We're going to go through our BA classifier. We're going to apply a forwarding class to your traffic based on the type of traffic that it is. But hey, if you go over your allocated bandwidth, according to what we've set up in our policer, then we're going to go and change that again. And we're going to give that a different forwarding class, which has a much lower priority. And we're going to up this loss priority, so it will get dropped if we get congestion on our network. Okay, so basically, as your traffic processes through the network, we're looking at all these different parameters, and we're changing forwarding class and loss priority as it goes through. There is this thing called a multi-field classifier as well. We then go into a forwarding policy, which affects queues and which queues different traffic goes into, how much memory those queues have, the priority of those queues as far as how they're processed. That goes right through our fabric. Then we go out, and we're going through policing again, multi-field classifier. There's our RED, which starts dropping traffic if we need to, shaping traffic, scheduling, and as it exits our network, we can actually rewrite the markings that we put on it on the way in, so we can send it out of our network without those markings, or we might send it out of our network with different markings, because the network that we're sending it to is going to treat traffic in a certain way depending on what we've written, the type of either forwarding class or loss priority that we've given it on the way out. So as the traffic goes through, we mark it up, we treat it in a certain way, we give it certain queues, we apply policing to it, we can implement these RED algorithms on the way through, and ultimately rewrite it on the way out with a completely different class if we need to. Okay, so traffic classification. There's a couple of scenarios here. We have the in-the-box model, which only uses a multi-field classifier. And then we have an across-the-network model, which uses a multi-field classifier at the edge and a BA rewrite and classifier in the core, which is behavioral aggregate rewrite in the core. The main thing is that devices will treat the traffic consistently right across the whole network. So there's different ways of approaching this, different ways of configuring our routers. Multi-field classifiers. This is an example of a firewall filter, which is a filter which says apply COS marking. So basically it says from a forwarding address. So in other words, saying if the traffic's coming from that address, then we're going to set a forwarding class which is called expedited forwarding. So we are actually marking up the packets. So actually writing this class into the packets themselves, all other traffic then accept. So basically if it's coming from that address, it's getting a particular class of traffic. That's kind of just one way of doing it. Then we're going over onto our interface here, and we are applying this filter as an input filter onto interface GE001. So here's traffic arriving at our router on that interface. It will be marked up if it comes from that particular subnet. It will be marked up as expedited forwarding. That's just an example, a very simple example actually, of how you can mark up traffic as it comes through your network using a firewall filter. Quite a simple example. Okay, so we are going to go through these behavioral aggregates here. This is a edit class of service, so we have some rewrite rules, INET precedence, so we got a default there. So this is basically just rewriting something onto our traffic, and this is another example here of another interface where we're putting a classifier on there and giving it a INET precedence. So these are just behavioral aggregate classifiers. We'll get into how these work in a bit more detail. So just sort of introducing the concept of class of service here. We'll get into the actual inner workings of it after lunch. So we're going to take a break, and when we come back, we'll get into actually how to configure this on a router, how it'll work, how to set up the queues, the priorities, the memory allocations, all of that, etc. So take a break, and we'll be back after lunch.